Okay, so for today, there's only one topic. Multivariate time series. To some extent, you can say that we did start that yesterday. Sorry, last week. Mentally yesterday. So what did we do? We looked at a system like this, where you had a univariate input, but then you had some noise as well. So now you have some input, xt, then you have a system. I won't write anything there yet. Then we add some noise. And we spent a lot of time last week on that noise. What could that be? And then we observed this as yt. That was pretty much what we did last week. Now, what if there's feedback not just from x to y, but also from y to x? How do we add that? Oh, I feel lucky this week. So what do? We take the y over here, and then we run it into a system, and then what do? Well, we add some noise. Let's call this n2, comma t. Maybe we should give this up here and a 1 as index as well. And then we take this and say that is xt. So what does this mean? If we can rewrite it. We should give these some names. So this here is, let's call this h1 of b as transfer function, and the other one h2 of b. So what happens here? If you have a system all at rest, all at 0, just to make it easy, then you do something to x from the external side somehow. Then you go through a system, so you have a transfer function there. You add some noise, and then you observe y. But then what also happens is that it goes through another system, you add some more noise, and then it becomes xt as well. So how can we write this? If we take the original equation was to say yt is equal to h1 of b as transfer function of xt plus n1 t, right? Likewise, if we do the similar thing for xt, how does that depend on yt? Well, that is then h2 of b on yt. That's what gets out here. And then I want to add the noise there. So this is what we have as a joint system here. So this is a bivariate system because we have two states. And now they're both input and output. So how do we represent this? Well, there are many ways of doing this. One thing that I always like when I have something that is multivariate is to write it on matrix form. Right now, if I have an extra equation for z, it would just be an extra equation. But I would like to have it all as matrices. So what I will do is I will take this here, move it to the left-hand side, and then I will try to put it into a matrix. And I will try to do it all in one go. And I'll do the easy one first. So I won't keep this order of the states, so I have yt, xt as my states. So for once I won't follow the alphabetic order at least. And then what I have as noise out here is n1, t, and n2, comma t. Then on the left-hand side, well, what I had already was a yt. So I need to have that again. So I need to have a 1 there. And then I have xt there. So I need to have a 1 there. That was the easy part. The rest is not that difficult either, right? I have my h1b on xt. So I have xt down there. I need that contribution in relation to my n1. So I need a minus h1 of b here. And then I need a minus h2 of b there. Do you all follow me there? Then I think I will show the same here. So basically what we have are 2 inputs, 2 outputs, and then we have 4 transfer functions. 2 of them are, you can say, quite simple because that's just the identity, but you can consider it generically as 4 transfer functions. So now let's take that one step at a time. I just said it verbally. What happens if you want to look at how does n1 and n2 couple to y? Well, what is that the same as? It's the same as looking at inserting up here xt up there in y. Right? So basically what I have to do is to insert xt in the first equation up there. So I have h1 of b on what is xt, and xt is h2 of b, yt, oops, plus n2 comma t, that was x of t, and then I have to add n1 t as well. Now, what I have to do here is that I want to isolate yt. But now I don't know these polynomials, so I can't just easily do the math. Well, I can to some extent start moving things around, but what would be beneficial would be to make the set transform of everything first. That is fairly easy in this case. So I look at y of z equals h1 of z multiply on h2 of z, and then I have y of z plus n2 z, parentheses close again. So that was the first bit, and then I have n1 of z at the end out there. Now I can use my usual calculation rules. So what do I have to do? I have to multiply h1 into this parenthesis. When I've done that, I will recognize I have one term on the right-hand side related to y, and all the rest is just noise. Let me just do it. h1 of z, multiply it on h2 of z, on y of z, plus, and then I have the h1 of z on n2 of z, plus n1 of z. And here what I can do is to take this term here and move it to the left-hand side. That will give me a 1 from that one up there, minus h1 of z, h2 of z, on y of z equals, and then what is remaining on the right hand side, h1 of z on n2 of z plus n1 of z. Sorry, h1. I think I said some n's where I meant h. Sorry about that. Now, what do I do next? I just have to divide by this, so multiply by the inverse of that. So I get that my y of z equals h1 of z n2 on z plus n1 of z divided by 1 minus h1 of z multiplied by h2 of z. So this model here, now of course I can split it out and take the division up on each of the input noises. And I think I did that when I wrote it over here. First going to the z domain and then solving. What is done there, further than what I did down here, is just to take this sum here and split it into two fractions. That's the only thing extra that is done here. So that means I have the transfer function from n1 to y here and from n2 to y there. So from n1 to y gives you a direct part that gives you the 1, but then there is kind of a dampening or whatever amplification by the system that gives you this fractional part. And for n2 to y, well, first it has to go through h1 before it can get to y. Therefore, you have an h1 at the top there. So I think it makes also somewhat intuitive sense. I think what is difficult intuitively to see is the 1 minus h1, h2. That was why I wanted to go through the calculation there, to see where that comes from. Now, this is of course trying to eliminate x. What if we just want to eliminate y instead? And say, what is the transfer function from the noisy input to x? Now, just look at the entire slide without focusing too much on any particular element. What happens? I'll go back and forth. Yes?
You switch n1 and n2.
Yes, and a bit more. But that is effectively what I did. The other difference is for the transfer function down here. What you have is now to get to x, n2 goes directly, whereas n1 has to go through h2 in order to get there. So therefore, what I do is you can say the nominator there, they are swapped. And it's also the other transfer function that is used. But, I mean, the whole thing is symmetric, right? You pretty much just, as you say, you swap. Whenever it says 1 in one, it says 2 in the other. And vice versa. The only difference is down here as well. So, that is, of course, one thing you can do. But that is effectively to create a univariate system out of a bivariate system. If you look at this representation here, is that a simple representation relative to what we have up here? If you look at the order of polynomials that you have in here, what happens when you do this? Try to take a multivariate system and make it a univariate system. Can you see what happens? There's one mathematical difference between the things that we have up here and using this here. Let's say that these transfer functions here, they are fairly simple, so they have a finite number of elements in them. Let's say that just a simple, let's say an AR model, AR2 models. So you have effectively have two non-zero contributions here, two lags that are non-zero. What would happen when I do this? I divide by something here. When you divide by a polynomial in Z or in B, depending on which domain you're in, what do you generally get? That's when you have poles. That's when you have infinite polynomials. Sometimes. At least you get a multiplication of things, so you may get something that is more complicated, at least. You also have another thing is, yes, you can say it's univariate, but you have two different noise inputs. One of the noise inputs, since it has the H2 and N1, it's no longer white. Does that make sense? So this noise that you add over here has color to it. And maybe I said it, I should rephrase this. This fraction, of course, I could keep it on the left-hand side and stick to this formulation here. But then if H1 and H2 are both second-order polynomials, and I multiply them together, then I get some other coefficients at least. So they're not exactly representing the same system, necessarily. Depends again, it depends on the model that you have. Now, you can also take the model written in the multivariate form and do the set transform of that, if you like. And you can pretty much do the same math. So, does anyone remember how would you solve this to get models for y and x? I want to isolate y and x on the left-hand side. How do you do? Yes? Exactly. You just pre-multiply by the inverse of the matrix. Now, do you remember how to invert a 2x2 matrix? Or is that something that's just ancient history? I always bring my paper to make sure that I don't type it wrong. Let's just be honest. So if I have a matrix A, B, C, D, and I want to calculate the inverse of this, then there are two parts in it. Now helping you a little bit. Yes?
The determinant might go.
Yes. A times D minus B times C. The determinant goes there. And then what happens in the rest there? Sorry? D minus B minus C and A. Yes, it's a conjugate. So what I try to remember is that you swap the order of the diagonal elements and you change the sign of the offline elements. That's how I was told in the good old days. But we can do the same thing with this fellow up there. So what we get is the determinant down there, which we recognize. And then what we get is that over here we have negative signs in front of our transfer functions in the off-diagonal elements. Now we have positive signs. And if you multiply in here, then you have n1 plus h1 n2. That's exactly what we have down here. And you can see that that is exactly what happened on the previous slide here. Here you have h2 and here I have a 1. Here I have 1 and an h1 for the corresponding. So that is exactly what you get out of this matrix. So that's where it comes from. So what I'm saying is, rather than doing a lot of univariate calculations here, we can just do it in a multivariate setting. And then you can, of course, if you want to write it in, you can just take this and multiply that into the matrix, and then you get something that doesn't look too nice, but it is at least a multivariate representation of the model. So what if we go back to last week and say we have a model of this form? So we have this Bok-Jensen transfer function model where you have some white noise that goes through some kind of an AMA model. And then you have another white noise signal. It goes through one model, and we call that an input. And then it goes through the system as such, and then we observe it. If we write this all up, then we can say, well, xt, that we get from there. Yt, we have described here as a transfer from xt and another add-on from epsilon t. So could we write this system that we last week looked at as an univariate noise model with some input? Could we write this on this form? Well, what do we need to define? There are basically a couple of ways to get around this. So if we look at all the fractions that we have here and just call them transfer functions. At first, what do we then have? If we define the state, similar to what we did up there, then we have yt and xt, and then we have, and I have the same order, epsilon t and eta t, and then we need to figure out what goes where. So what happens to yt? Well, you get yt by taking xt and running that through a filter. But you also need to have, to keep it on the left-hand side, you have the yt, you have an indicator there, and you have an indicator for xt as well. And then we have a transfer from xt to yt. Let's just call that h1. Let's call it xy of b. Now, what else do we have? To get to yt, we have some noise that goes in there. So we have a transfer from epsilon to y of b. We have no transfer from eta directly to y, so we have a 0 there. We have no transfer of epsilon directly to x, so we have a 0 here. And then we have a transfer from eta to x, and let's call that h eta x of b. Now I skipped one element. What should that be? What does that element say something about? Yes? So what does this element explain? It's the contribution to xt from yt. So how does xt depend on yt in the particular model here? It doesn't, exactly. 0. It was a trick question, maybe. So here we have a bivariate representation of what we looked at last week. Of course, what we could do would be to take all these fractions here and multiply by everything that is below the division there, and then we will get, you can say, some more clear armor models. I don't know if you can see this. Here, if you have these as, you can say, polynomials that are different from just the indicator, then you would have that these operators here would have infinite number of coefficients or infinite support. But if you kind of move those elements to the right, to the left-hand side, then you can have something, you can say, that where things are all finite number of parameters. But that's another story. What I want to get to is the generic setup here. And you can still do the same manipulations, if you like, by multiplying through by some polynomials. And I think that's what I get to here. If you do the multiplication, then you have the delta of b multiplied on everything in the first line. So you have it there and you get it there. Then you have phi epsilon of b, you get it there and you get it there. And the second one is fairly easy. You just get phi eta of b on xt and a theta eta of b on eta t. So you could also go from there and write the same system. Moving this term here to the left-hand side, that is also a matrix representation, and we can write that as an equivalent of this formulation here. The big difference is that here, some of these transfer functions here may, depending on the order of the different polynomials in the denominators here, they may be infinite, whereas in this formulation here, you know that, well, the order here is the same as it was up there, effectively. The interpretation, when you multiply things together, of course, so everything here, if everything up here was finite, then everything here will also be finite, right? Okay. So here's the matrix representation of that. And I say one thing that you just have to note, that is generally you always have a leading 1 in the diagonal. I made it very explicit in this notation and also up there. But you always have a leading 1 here because you need to have yt and xt in the equation. You cannot just ignore that you're modeling the current time. So you're looking at how does the current time depend on things. That's just one thing that sometimes may be masked a little bit. So I just want to emphasize that. So to be more generic, of course, everywhere there's a 0 here, you can make a polynomial b. So what do they represent, those non-zeros? If this was non-zero, well, it represents that yt influences xt, or previous values of y influences xt. Just as we had in the first example up here. So that's the feedback around. Now, over here means that you can also get a non-zero correlation. And you can actually do that in different ways. You can do it by adding something there at time t. But you could also say that these two signals out here, it's a multivariate white noise. So they may have correlation between them, but still being white. Univariately, they're white, but they may still have correlation. I prefer to add it as a matrix here where you say what is the correlation structure. So, basically if you look at this here, then you have something on the left-hand side and something on the right-hand side. That's just the same thing as we did for armor models, right? So we can consider it a phi polynomial in matrices on YT generically with some mean value structure as well, which we will generally just assume to be 0, but here I just included it. And then likewise on the right-hand side, you have a theta polynomial epsilon t. So each of the individual here time series, so YT in the bivariate case, what you could have done, I'm not saying it always meaningful, you could transform, say, xt without transforming yt, depending on what you're modeling. You could take the log of one state but not of the other, if it is meaningful. I tend to say, if the things that you have as state in a model, if some of the states are of the same nature, let's say they are prices of something, then if you want to do a transformation of one price, you should also do it to the other. But if one of the remaining states is, say, an interest rate, doing a log of the prices does not necessarily mean that it's meaningful to take the log of the interest rate, because it's a totally different thing. Maybe you wanted to take the difference as well of some things, but not of the other. That is fair game. So there's a lot of flexibility there where you have to look at the individual series and say, what do you want to do as for transformation? And remember one thing, that's the same thing for the univariate models. When should you transform? Well, what is it that you're looking for? What are the assumptions at the end of the day that you hope to fulfill? Let's just go for the univariate models. Yes?
The time series stationary of order 2.
You want to have stationary? Yes?
Well, I mean, the variance also is only transform if the variance is not the same.
Exactly. So if the variance depends on the state of the value, that's one case where, and it's somewhat the same as saying being stationary of order 2. Those two statements are effectively the same. So variance homogeneity, so the variance is independent of the state. That's one thing. It also being skewness and other things that you could have that could also say that when you look at the residuals from your model and you see some skewness there, then you should consider doing a transformation to correct for that. But you should not just look at the observation and say, I definitely need to do a transformation. You should do a model first and try to model the data and then see if you fail to do that, then you make a transformation that may help you out. Now, if you made a model A here with a transformation and a model B without, how can you say which one is better? Yes?
I guess it's a complete analysis of the residuals. The whole picture.
It is exactly the whole picture of analyzing the residuals to see if which one of the transformations gives you the best resemblance of white noise, because that's the underlying assumption. The number of parameters and such AIC and all those other things that you have used to develop your model, you cannot use those when you transformed your response. That's the important thing. Anyways, so that works both for univariate and the multivariate. When you can say a simple transformation would be to divide all numbers by 10. And of course, then the noise signal is also different. So you cannot use any of the parameter estimates. And I think that's the one thing that is very tempting to do. That is to compare some of the numerical values, but the only thing you can actually use to compare the models is to figure out which one is more adequate by looking at the white noise. You can say test for white noise. Which model is better? Yes?
So if the residuals are skewed, then what transformations would be proper to use?
Yeah, that again depends on which way the skewness is.
I don't know, if you look at a cuckoo plot.
Yeah, but in a QQ plot can be skewed both ways.
I got something else.
Just to say, I know some of you have mentioned the Box-Cox transformation. If you know what that does, it can help you figure out what to do. What I generally say, what most often happens, let me put it that way, is that you have that the variance is greater when the values are greater. That was what I discussed last week. Doing the log transformation of your data will compress the variance for large values relative to small values. So in that sense, if you have that kind of skewness where large values have larger variance, then you should do a log transformation. But again, it depends a lot on what you're modeling. You can also do, if it's the reverse, you want to do 1 over x as an example. So there are many different things you can do, but what you should generally look at is where do you want to inflate the variance relative to other places. And then you should do a transformation that does exactly that. So if you have a relationship between the variance that you observe and the variance that you want, then you just have to do, as we discussed last time, that the variance of a function of a random variable x, that is, in a univariate sense, and then you want to evaluate it as x equals x, and then I need to square that thing, and then take the variance of x. So if you want a transformation, you should look at, well, if you have the derivative of the transformation that you want to look for, that's the transformation that you want to use. So if you know what you want to do, you should say, well, if that's the derivative of a function, what is then the function that I'm looking for? So that's where the log transformation gives you a 1 over x as derivative, and thereby it compresses the variance here relative to there. Yes?
What x's are capital?
Yes. So this is, I think I would do it like this, but I mean, this is how it is, but what you do is, in practice, then you take the variance here and you evaluate it. You would generally condition everywhere on x being lowercase x. You will use this for observations. So maybe I should do it like this and say, what you do is, this is how you transform the stochastic variable, but then in practice what you do is that you use the observed values, because you condition on those when you do the transformation.
I was looking at this with TA last week.
Yes?
Then we got the
No, so exactly that. What I'm saying is that in practice, what you end up doing is that you evaluate this. These are in particular values. So what you do is that you look at when you have observed. So this is the generic transformation. But I agree, you need a number here. That's what you're saying, basically. So you need a number. How do you get a number there? Well, you need to use the observations that you have. So you need to do everything conditioning. Now I observed 10. What do I then do? Well, if f is the log transformation, then what I will look at is what is the variance of log of 10. Now that the problem is now it becomes a number and not a random variable. So that's not so good. Because now this is the variance of this is 0, right? So that's why what you often do is that you say you keep your random variable here, and what you do is, well, you just pick the appropriate value here and say, so that's 1 over 10 square, and then the variance of x. This is what you end up doing. But you do the transformation. This is just how, basically, most often you're not doing this calculation. In practice, what you're doing is that you're just transforming your observations to get some new observations, and then you just use those and model. This transformation is to understand what are you doing to the variance structure. Effectively, what you do, you're not doing this calculation as such. You're not calculating the variance at any point in time, typically. But what you in practice, what you consider is, well, what is this derivative for particular values? So I can totally understand your question, and it's not so easy to actually explain. Because you're looking at the variance of a random variable, how is that changed when you do a transformation?
So conceptually, just to make sure I get it right, we're not using the formula just to get an idea of what happens.
What we're doing is that we're looking at which transformation has which derivative, and then you want to pick a transformation that has the characteristics of the derivative for the range of x's that we have that can give us the feature that we're looking for. Yes, so we're not as such, typically, at least here in this course, we're not using it for calculation as such. And if you're just doing the calculations, well, then this is what you're doing. But you will be conditioning on the actual value of x to do calculations. If you are going to do something, then you will add a condition on uppercase x equal lowercase x there. Or you evaluate it at uppercase x equal to lowercase x. Okay. How far did I get here? So, in general, what I also said before, the diagonal elements, both on the left-hand side and right-hand side, they have leading terms of 1s. So you have a identity matrices as the leading terms there. And then the off diagonals typically have leading terms of 0. So this typically start in B. So it means that typically yt does not depend directly on xt. It depends on xt minus 1. You can consider it in a physical sense that it takes some time to get through a loop up here. So you don't have the information immediately. Okay, and these polynomials up here, of course, they have elements that are polynomials in the backshift operator. I'll show you that again. The epsilon noise here, well, has a covariance matrix again that may have correlation in it, as said before. So you can do things by placing things out here. That gives you correlation between this effectively in the output, or you could say that these have correlation. If you say that the leading terms off diagonal here are zeros, that means that the b to the 0 order is a 0 here. Then if you want to have correlation, then you should put it in the correlation structure of your epsilons. Because otherwise you have two ways of doing the same thing. Now, if you want to estimate two parameters, but there's actually only one, what happens then? You have a numerical problem where there's an infinite number of solutions. Right? Does that make sense? It's, I think the most simple example of that is if you just have an MA1 model, so you have actually just, if we have this model, it's very simple, right? Here I have one parameter that is sigma epsilon. I have to pick a value for that. And I have to pick a value for theta 0. The only thing, if I look at some observations here, the only thing I can say something about is the product of these two. So therefore, we typically fix that to be a 1, because then we can estimate this one. If I let both be free, I cannot estimate them, because I have infinite number of combinations. I can see some of you got it, and some of you are hanging there. Ask the question later, and we can discuss it in a break. So, what we looked at in the very first lecture was this air pollution case with NO2, nitrogen oxide, and nitrogen dioxide. And we, at that point, just postulated this model. So what is actually, given what we know now, how would you, which kind of model is this? We can take it in pieces. So what do we have there? Which kind of multivariate armor model is this? Yes? It's an AR1 model. So what more did we said? It's a bivariate. So it's not a general multivariate, it's just bivariate AR1 model. Are everyone on that page? So, of course, we can write that in different ways. If we do it, you can say, within matrix notation, we have it like this, and we can take the coefficient matrix and put it on the left-hand side, and if you use the backshift operator, we can represent it in this way as well. I think that's fairly straightforward. But just to show you an example of a model where you indeed have in diagonal have a leading term of 1, in the off diagonal you have a leading term of 0. So that is what you usually have. Yes?
Is it possible that, say, because right now x1, x1 t minus 1, would it be possible to have, say, x2 t minus 2, so you have that x1 is an AR1 model and x2 is an AR2 model?
In that case,
Because then you cannot,
if, yeah, you can always do that. You'll just have some zeros. So basically what you're saying is if the x2 is an AR2 process and x1 is an AR1 process, basically you just need to add plus something b to the second power in the lower right hand corner in this matrix here. Right? So you can do, and that is, you can say, in that case, it's maybe nice to have it in this case, in this formulation, whereas in this formulation here, you just have a generic xt minus phi 1 xt minus 1 minus phi 2 xt t minus 2 equals epsilon t. And then you would not be able to see that it's only in one of the elements that is non-zero here. So, but you can say it's equivalent. And that's actually one of the things we'll get back to next week. Often you have a lot of these coefficients to be 0 because you don't need to have the full order of the model everywhere. You just needed some selected places. And that's the purpose of looking into that. That's next week. So, I think the last slide before break. Stationarity and invertibility is very similar to what it was for the univariate models. Do you recall what you did for the univariate models? For stationarity? It involves a set inverse as a hint. So you're looking at the poles inside the unit circle. So you put set inverse, phi of set inverse equal to 0. You solve that for the roots of that polynomial and see if the roots are inside the unit circle. Exactly. Now, when you have a multivariate system, rather than just doing phi of set inverse, you take the determinant of phi of set inverse and solve that equal to 0. Same, right? And the criteria again are all the poles inside the unit circle. Invertibility is the same thing, are all the zeros inside the unit circle. It's just a determinant of theta of set inverse equal to 0 that you solve, instead of just theta of set inverse equal to 0. So, and the nice thing is, if you have a univariate model and take the determinant, poof, you just have the operator, right? So, those criteria are pretty much the same. Of course, a little bit more complicated if you have a higher order model, but let's not focus on that. I promise to take a break now. Let's do that and resume roughly 7 minutes past to make it 10 minutes.